introduction, and thank you for having me here. And I'm gonna try to stick to 30 minutes. But before we start, I would like to do an experiment, and I hope you don't mind that you guys close your eyes for a moment. And I want you to think that you're a fish or a dolphin, your favorite marine organism. And you can see, but you cannot see very well underwater. So let me increase the volume, please. This is not what a fish or a dolphin will hear, but it's actually very noisy. How does all this noise make you feel? But imagine if you were in a place this noisy and you're trying to say something to someone on the other side of the room. What are the strategies that you have to come up with to be heard? You either have to scream, right? That means you have to increase the volume of your voice, be louder. You either have to lower your voice so your voice sounds like this and maybe carry it farther away. You may maybe elongate the vowels, like ahora, something like that, so that you can actually get the message done. And these are many strategies that actually not just marine animals, but also terrestrial animals have evolved to deal with masking in their natural environments. And they can be very handy in an environment that is increasingly noisy because we are now there too. And so in my lab, what we're trying to do is to use underwater technology, which has really become available for everybody. It's cheaper and it comes in different shapes. So this one, for example, is called a sound trap that you pass around. It's very simple. You put your memory cards, some batteries, and these can last for 3 to 4 months, depending how we program them. Or if you want to be, more dedicated to animals that have very quiet signals, like fish, right? You can use small things like this and have multiple. This is like maybe $150. And you can have several of them and a coral reef, and you can record different aspects, differently parts of the coral reef, and get a sense of the sounds that are there. In my lab, we work, I call it the ONDAS lab, but a lot of people know us as the whale lab. And we do whales, but I also am interested in the space in which these whales live. So we are interested in understanding from an evolutionary point of view, what are the signals that these animals are producing, right? What's the collection of sounds that they're producing? And what are the factors that over evolutionary time has shaped their vocalizations? But these animals are not alone, right? They live in a space that is also very noisy, naturally noisy. So there's wind, there's rain, there's wave action, and there are many other marine organisms that produce sound. We have the snapping shrimp, we have a lot of fish, make all sorts of sounds for a number of reasons. And so we want to understand how these environments, these rapid changes in the environment, are shaping their vocalization in real time, and how we can regulate sound. So if we understand the variation of noise through time and space, then we can have a model that can help us then later make decisions how we can regulate noise, which, as you're going to see, is very hard to do. So given this context of the GON Institute, that you guys are looking for solutions, right? That's the mission, and to tackle very critical environmental challenges. My environmental challenge is underwater noise. And so today I'm going to focus my talk on the challenges that these animals are facing today as the ocean is getting noisier. And I'm going to tell you about how I'm tackling this problem by initiated initiative that's called ONDAS. ONDAS means waves, right? It could be sound waves, ocean waves. And this initiative involves everybody from government to NGOs to students to tour operators. Everybody is participating in this program so that we can get a sense of how noise is impacting marine organisms in several Central American countries. So this is gonna be my major talk today. So as you can imagine, the ocean is not a silent world, as Jacques Cousteau introduced it many years ago. It's actually very noisy. There is biological sounds from all different sources, from seals to whales to snappers and sea urchins, and many other things that we're still just learning about. Also, geological noise from wind, rain, wave action. Those are very important. Earthquakes also contribute to those NGOs. And then we have, and since the Industrial Revolution in the mid-1800s, the introduction of human noise in aquatic environments, and that has been increasing very, very rapidly. So this is just to give you a sense. This is commercial. This is only commercial shipping lanes and how their activity from, I think this is from 2015 to 2021. And the challenge here is that these type of signals are very broad in frequency. So it goes from 1 hertz to about, 100 or kilohertz. It depends on the size of the ship, depends on the engine. There's a lot of variation on that. But you can imagine the impact of this noise on a global scale. Right? There's organisms from pelagic to coastal environment. Coastal environments tend to be even more noisier because that's where the ports are. So there's a lot of noise going on there. And so it's a challenge. And we know that this is continuing to increase because everything that we're wearing today has been transported via the ocean, right? So as we get new cars, new computers, everything is being transported. So the demand that we have and all these goodies is increasing the number of ships transporting all these things. So a few years ago, there's George Fritz did a really nice study to kind of see how that increase in GDP, but also increase in the number of ships that are transporting all these valuable things to us, really was related to noise. And what he found is that from the 1950s to 2007, there has been an overall increase of 19 decibels. But let's say that is about 20 decibels. But because we measure volume, right, or noise and decibels, which is a logarithm scale, that doesn't mean that it's the doubling. This is an increase of 10 times the baseline of natural noise. So if you look at this scale, for example, the supertanker, there's a difference of 30 decibels. So this means that this guy has about 100 times the sound energy than a tank. And imagine many of these in the ocean. So the amount of energy that is coming from human activities is very impressive. And the main concern is that there's a lot of potential for masking. There are other impacts beyond masking. So if you don't know, you've never heard any other animal, apart from dolphins and whales, there's a bunch of marine organisms that rely on sound. So you're gonna hear first sea urchins, which is a byproduct of their motion. You're gonna hear some snapper and shrimp, a lobster, a couple of fish, and then we'll hear the dolphins and the whales. And notice that they have a relatively broad frequency, and all this frequency, if it was a tanker or even a fishing boat, it will cover all this frequency range. Start the dolphins, the whole feeding at first, and then you hear some signals at the end. Okay. So we know now there's there's enough evidence that shows that, yes, there's masking happening, but there are other things that are happening as well. We now know that there's a lot of pelagic larvae from, crustaceans and mollusks and fish that use these natural sounds of coral reefs to find these high quality habitats and continue their development there and establish themselves there. And we also know that in areas where there's a lot of anthropogenic noise that is interrupting their mass signals, it makes it very hard for larvae to find this habitat. Also, when there's a lot of noise in some of these environments, there's a lot of these animals leave this habitat. So then the natural noises of these environments is lower, and so there's less an indicator that there are changes in the suitability of the habitat. So we know a lot of this happening. And we know also the animals have evolved a number of strategies to cope with these changes in the environment. We know that sound is super efficient in water, so travels fast. You can use it any time, loses very little energy. And it's just simply very convenient and in a space where you can barely see. And we know that a lot of organisms have evolved these dependence on sound. So it's not simply that they can rely on other cues, they rely strictly on acoustic sound. And the problem is that anthropogenic noise from human activities also benefit for all these properties. So we know that then, depending on the frequency, these sounds can be detected farther and farther, because as the ocean gets warmer, the sound speed increases. So now they can reach to even farther distances. And there are several effects that have been shown. There are behavioral disturbances that have been shown in many different groups. There are problems of or changes in the fitness of populations. There's also changes in community that have been reported, masking, as I mentioned. This is a review that came out very recently in light gray. This is showing you the overlap of anthropogenic noise. This is the frequencies at which these animals here in dark blue and produce their own signals. So there's a lot of overlap in here and what they're producing. And in dark gray, it shows all the studies that for which this effect has been supported, statistically supported. So you can see the variation, for all the lineages that are impacted by anthropogenic noise in one way or the other. And so that can inspire this project. I was living in Puerto Rico at the time. That's when I met Aura. And I was a postdoc at the Argumon project. At the time, was funded by NSF. And they were deploying stations to record soundscape in different types of habitats and forests and savannas in Puerto Rico. So I wanted to do the same thing in the aquatic realm, but the technology wasn't available there. So I started kind of testing different things. Finally, in 2016, this time there was like this bloom of technology. It was getting cheaper. And I got a fund from Conservation International. And we began with a couple of recorders deploying it and protected, outside protected areas. And suddenly everybody was interested. The fishermen, the tour operators, everybody wanted to hear what the underwater world sound like. And little by little, we began to get more funding from different institutions. We just got this one in collaboration with the government of Panama. This is about $300,000 grant to set a network of these underwater recorders in different outside and inside protected areas along the coast of Panama. And we have right now, let me show you, these are just some of the people that participated. It's incredible what people hear. What's going on, that you put a hydrophone in the water and they hear all these incredible sounds. It really makes a difference, especially if you're a tour operator, that you use your boat, right, to follow animals and take people to scuba diving, to coral reefs, and realizing how your boat is detected, received by animals makes a big difference. So all of them are helping us. I can't be there in the water all the time, so they're helping us to deploy and recover this soundtrack. This is the one that I show you that we can put in a station. We have multiple stations right now. We have 9 underwater recording at this moment. and we'll pick them up next year. So this effort, now we have deployed since 2016, about 29 sites. This is about, and I have to do the math, but it's about 3 million minutes of recordings through different scales, temporal and spatial scales, which is incredible and gives a lot of people the opportunity to really understand what is happening underwater, not just in terms of anthropogenic noise, but we can also use a number of new indexes of acoustic diversity to get a sense, a very quick assessment of what's in a particular habitat. And so this is being used. This is the Arbimon platform. Right now, only have like 350,000 minutes. The idea is to make it open access so everybody can go in, from teachers to kids to researchers, students, to go into there and just listen to what's happening at midnight in a particular location. It comes also, they are developing a number of machine learning tools. So for matching and identifying species and also measuring soundscape. So it's gonna become a really important and free tool for a lot of people. So getting the recorders there is the easiest part. Recording them is really easy. We have lost only one, and all this time, people really, participate in this, so we haven't had any issues. But when we bring all this thousands and thousands of recordings, that's the challenge. And that's where we are stuck at the moment, because we're trying to find machine learning tools that can help us do a lot of things. One, we want to have a sense of the overall soundscape, how that changes in time and space. But we also want to be able to identify what is in each of these things. So we need to go to the field, we follow the animals. Right now we're focused on marine mammals because it's easier to do that. And so with the animals, then we can create templates for algorithms, train them, so that we can then later try to identify what are in these recordings. We are also, so that will give us a chance to kind of look and identify acoustic predictors that can help us identify the species. But in dolphins, there's a lot of overlap of frequencies. So just the frequency doesn't help. We need to know what the contours look like, and if there's variation in the contour, that makes the entire collection of sounds. So we're using unsupervised machine learning to train and to identify the composition of the vocal repertoire, so that can also facilitate identification. And then the hope is that then we can later move to fish. In a lot of these communities, there's a number of fish that make sound. They're actually even more exciting than dolphins and whales. That's the next step, hopefully, in the next few years. And all this is done in collaboration with, these are students here at UVM, graduate students, undergrad students, students in Costa Rica, in Panama, and the Pure courses have given me an opportunity to involve students in this kind of research. So they take part of the data and they can make it their own and contribute to the overall goals of this initiative. So I'm just gonna quickly give you a few examples of how we use this. The first one is an example of how we've been training and try to use not just acoustic parameters, but also that collection of the repertoire to help us identify species. This is a very fine level. We're trying to identify 2 subspecies of pantropical spotted dolphins. And then I'm gonna tell you what happened when the pandemic hit. We were just very lucky that our recorders were still underwater. So we had the opportunity to record what happens when most people leave the place, right? And it's not that there were no boats. There were still some people going out. But the magnitude of change, we wanted to see what happened. What do animals do? We heard people detecting birds farther, like they perceived that they were more birds, but they're actually detecting it farther away because there's no traffic, right? So we wanted to see what happened. So the first one, and it's very general, and I can talk to you in more detail later. This was the second master thesis of Manali, and we got recordings from those recorders that I mentioned from NOAA. from a collaborator, Noah, who had been recording the offshore, and we collected data from the coastal dolphins. We got data from 3 different countries, and then those points from the ocean subspecies. So this is spotted dolphins were in the 70s impacted by the tuna fisheries. They died in big numbers, and the reason why the National Oceanographic Administration did so many surveys from the, I think it started in the 70s, and I think some of the last ones were in 2010, I want to say. So there's a lot of data, acoustic data collected by them, and with ours, we wanted to kind of check what is the vocal repertoire of these 2 subspecies. The coastal is very faithful to that segment, and they are morphologically different. So we wanted to see, can we tell the 2 subspecies apart? So we did a machine learning analysis where all the signals are categorized. This is a program called R-Work that takes the signals, stretches it, shrinks it, and creates categories based on the frequency contour, and then it learns. And then as it learns, it begins to correct itself, and then creates new categories or unify categories depending of the shape, right? And you can tell them, well, I wanted you to put things that are similar, about 92% along the contour, or 96%. And so we did that, and then we use these categories and combine it with ecological tools to measure the diversity of that repertoire. And as you can see, they have pretty much the same diversity. But when we look into the composition of these repertoires, we found some differences. The coastal dolphins that live in a very noisy environment, not just because they're corals and mangroves, but there's also the ports and the boats and the whale watching and fishing happening in those waters, tend to produce signals that are upsweep signals, which are relatively simple in their contour, which maybe tend to propagate much easier than if you have something that is more modulated. It can lose energy faster in a noisy environment. So while the diversity is pretty much similar in the context of the different kinds of signals that they can produce, the composition was different, and also the frequency. So in coastal environments, these animals are producing low frequency sounds, which tend to propagate relatively faster or better than high frequency signals. So this is going to give us the opportunity to test these methods and this long-term data to see if we can identify at the subspecies level. And then the pandemic hit. This is a paper that just came out recently that shows the change in sound energy from 2020 and 2019. So you can see the low noise levels compared to previous year. So this is before. This shows a trend and increase in noise levels in the ocean, and during the pandemic, you see that drop. Right? This is worldwide. In Central America, where we have our sound traps, the main source of sound is actually associated with dolphin watching and whale watching. And that's because this activity has become very good for earning money. Like, it's less dangerous than fishing. It's also, it's more predictable than fishing. And also when it's El Nino, like right now, fishermen have the opportunity to do this in a much, safer way. So, and there's a study that is quite old, needs to be updated, that shows that in Latin America, there was a rapid increase in whale watching activity specifically than in any other tourism activity, or when you compare it at the global level. So we wanted to see what happened, because the first thing that stopped was people traveling, right? And Central America is a very important place for people to vacation. If you see the number of passengers and airlines, it dropped almost to 0. And so we wanted to see what happened when there's no tourism. You're gonna hear the first thing, just to give you a sense what a dolphin is hearing and why we worry so much. This is going to be a boat that is about 100 meters away from the animals. It's an engine that is quite decent, 115 HP, and this is when the boat is really close, about 5 meters. This is typical, there are regulations, but they still want to get people closer to the animals and be always the first. Look at that, it's one boat. But closer. So imagine now a place where you have 20 boats following the same whale or the same dolphin. Right? So we wanted to see what happens when these kind of behavior and interactions, although short-lived, if you live them many times a day, it can be very stressful. So we focus on 2 places, Boca del Toro, which is a place where we have been studying these animals for almost 20 years, and then Costa Rica, the Pacific side. I don't know if you've been in the Osa Peninsula. There's an island called Caño Island, which is a very important habitat for southeastern humpback whales that migrate from the Antarctica all the way to Central America. It's become a very important place because these whales are recovering. So we get so many whales there that there's a whole industry. The government just made them declare a law that they are of public interest, which is going to make people even, be aware. So the first paper, so this is a publication. Emma was also a Sailor Master student. She did the same analysis as Manali. We got the data, used the machine learning, created categories, and we look at the diversity of the repertoire before, in blue, the lockdown, and during the lockdown. And you can see that independent of the measures that we use of repertoire diversity, during the lockdown, there was an increase in diversity. Now, here's the thing. Dolphins produce individual whistles. So each animal has their own whistle. That is like their name, right? Or like someone that you recognize your mom's voice. So what this could mean is that these animals, we have either more animals present or more vocal activity happening. But because we know these signals are very different and they're unique, it's very likely that suddenly the bay is full of animals that is being used much more for these animals. And you can see that in decrease in noise levels. There's more variation probably because now we're detecting other things that make noise that we couldn't detect before. So low levels, there was a decrease in the number of boats. There was also a shift because it's an archipelago. People have to still go to the hospital and buy food. So it's not like there was a big drop in the type of the number of boats, but the activity was so different that also that changed the noise levels in the air. And with the whales, we had data for before, during, and after, but the problem with the after is that this is 2019, 2020, 2021. And as you can imagine, a lot of people couldn't recover in 2021. So 2021 looks very similar to the lockdown. We have now data from 2020, 2023. So we're gonna look into what happened. But overall, you can see the noise levels during the pre-lockdown are pretty high, doesn't matter what time of the day. The lockdown and post-lockdown look very, very similar. There's a lot of variation happening there. And then when you look at the boats, you can see the boats, most of the activities between 6 and about 4 p.m. This is the pre-lockdown. So this is before lockdown. And this is after lockdown. So you can see there was a drop in the detection of boats when the pandemic, the lockdown pandemics were happening. And here are the whales during the lockdown. You're basically seeing in the entire time, there's a little drop, which is natural to them, because usually during daytime, they kind of lower. But really, compared to other years, they're singing the entire time. Whereas, the other years, there's a lot of more variation. So now we want to have more data to see if these drops are associated with the changes in both, so that would be nice to have a nice model that we can account for other variables. And this particular study was published in Revista Biología Tropical, which is a local journal, that we wanted to make sure that local scientists had the opportunity to publish in their own language or in English. And everybody ended up doing it in English because there's a self-awareness that if you write it in Spanish, nobody's gonna read it. So we made sure that our reviewers understood that and that the role was, yes, look at the science, but also let's help the scientists to produce something good. So this paper was published here and contribution to that effort. Now, as I mentioned before, the challenge that we're facing is that these noise levels are going to continue to increase, but we also know, and based on our recent model, that the ocean's getting warmer, and that not just, just if you look at map, it's the latitude, but if we were to see this in the context of depth, it's also getting, deeper waters are getting warmer as well. So sound transmission is being impacted, right? So now in warmer waters, sound tend to travel faster. So this sound propagation is changing and is reaching probably farther away than in the ocean. So the impact is going to increase. And there's been a lot of concerns about this. In 2019, the United Nations had a summary of, at the moment, what we knew, what we thought of things were going on and the impact of noise. And there's a lot of push for starting to think about how do we regulate noise, which makes it really hard because of the changes in sound transmission, right? We'll have to regulate not just the number of boats, we have to look for new technology that minimizes the noise in the ocean. So my goal, I hope, is that you have a sense now that animals produce diverse signals that are very important in their survival. That we have seen an increase in underwater noise levels, and that's a big change in the acoustic environment, and that anthropogenic climate change is going to exacerbate the effects of underwater noise. And I'm hoping that this ONDAS strategy will attract other people too from other fields, right? Because we need people from other fields that can help us to understand the dynamics of underwater sound, make predictions about if we go in this direction, how animals are going to respond. Can we make predictions based on what we know about their communication? And what kind of designs can we establish that are dynamic? Because these changes are not stable in time, right? There's variation, and with climate change, there's going to be a lot of dynamic happening that changes dynamics, management strategies and policies that can be adaptable and over time. And that's what the kind of questions and kind of ideas that I hope to bring to the Institute and can brainstorm with a lot of